Imagine crossing an ocean in a wooden ship, with nothing but stars to guide you, waves that could snap your vessel in half, and absolutely no idea what lies beyond the horizon. No GPS, no radar, no engine, just wind, wood, and an insane amount of courage. Between the 1400s and 1500s, Portuguese sailors did exactly that, and they didn't just survive, they changed the world forever. But here's the thing, most people don't know. Their success wasn't just about bravery. It was about revolutionary engineering that was centuries ahead of its time. Today, we're diving deep into the science behind the ships that conquered the unknown. But before we set sail on this journey through history, if you love learning about the brilliant engineering and science that shaped our world, smash that subscribe button and hit the like button right now. Trust me, you don't want to miss what's coming next. Now, let's get into it. Let me start by talking about the ship that started it all, the caravel. Now, when I say the caravel was revolutionary, I'm not exaggerating. This wasn't just another boat. This was a masterpiece of engineering that solved problems shipbuilders had been struggling with for centuries. Picture this. It's the early 1400s, and if you wanted to explore the African coast, you had a serious problem. The ships of the time were either too big and clumsy to navigate close to shore, or they were small fishing vessels that couldn't handle ocean voyages. You needed something that could do both. Nimble enough to explore coastlines and rivers, but tough enough to survive the open Atlantic. Enter the caravel. The Portuguese caravel was typically between 50 to 70 feet long, relatively small by ocean-going standards. But what it lacked in size, it made up for in brilliance. The design was shallow drafted, meaning it didn't sit deep in the water. This was huge because it meant you could sail close to shore, explore river mouths, and navigate shallow waters without running aground. Try doing that in a traditional medieval cog, and you'd be stuck on a sandbar before you knew what hit you. But the real genius was in how they balanced this shallow draft with ocean worthiness. The caravel had a narrow hull with a length-to-beam ratio of about 3.5 to 1. In plain English, that means for every unit of width, the ship was 3.5 units long. This made it sleek and fast, cutting through water with minimal resistance. The physics here is beautiful. A longer, narrower hull reduces drag and increases speed, following principles that wouldn't be formally described until centuries later. The construction method was equally innovative. Portuguese shipbuilders used a technique called carvel planking, where wooden planks were laid edge to edge on the frame, creating a smooth hull. This was different from the overlapping clinker method used in Northern Europe. Why does this matter? Because a smooth hull moves through water more efficiently, reducing friction and allowing for higher speeds. It's the same principle that makes modern boats sleek rather than rough. And here's something that blows my mind. The caravel could carry about 50 tons of cargo while maintaining its maneuverability. That's a perfect balance for exploration. Enough capacity to make long voyages viable, but not so much that the ship became unwieldy. The Portuguese had essentially created the sports car of the 15th century. Now, a ship is only as good as its ability to harness the wind, and this is where the Portuguese showed their true genius. They took the lateen sail, a triangular sail that originated in the Mediterranean and Arab world, and turned it into the key to conquering the Atlantic. Let me explain why this was such a big deal. Before lateen sails became common on Portuguese ships, European vessels mostly used square sails. Square sails are great when the wind is coming from behind you. They catch a lot of wind and push you forward efficiently. But what happens when the wind isn't cooperating? What if you need to sail against the wind or at an angle to it? With square sails alone, you're basically stuck. You either wait for the wind to change or you row, and good luck rowing across an ocean. The lateen sail changed everything. Its triangular shape, mounted on a long yard arm, allowed ships to sail much closer to the wind, a technique called beating or tacking. The physics behind this is fascinating. When wind hits the curved surface of a lateen sail at an angle, it creates a difference in air pressure between the two sides of the sail, similar to how an airplane wing generates lift. This forward component of force allows the ship to move forward, even when sailing at angles as close as 30 to 40 degrees to the wind. The Portuguese caravel typically had 2 or 3 masts with lateen sails. This configuration gave captains incredible flexibility. Need to sail up the African coast against prevailing winds? No problem. Tack back and forth. Need to make a quick turn to avoid rocks? The responsive lateen rig made it possible. This wasn't just convenient, it was essential for exploration. It meant Portuguese sailors could go places and return from places that were simply inaccessible to ships with only square sails. But here's where it gets even more interesting. Later Portuguese ships, particularly the larger carracks, used a hybrid system, square sails on the main masts for downwind speed, and lateen sails on the mizzenmast for maneuverability. This combination was like having both power and precision. The square sails would drive the ship forward when conditions were favorable, while the lateen sail provided steering control and the ability to adjust to changing winds. The skill required to operate these sails was immense. Sailors had to understand wind patterns, know how to adjust sail angles precisely, and work together as a coordinated team to tack the ship. The crew would have to swing that long lateen yard from one side of the ship to the other, a dangerous operation that required perfect timing. One mistake and you could have the yard crash into the mast, tear the sail, or even injure crew members. As Portuguese explorers pushed further into the unknown, they realized they needed something bigger than the caravel. They needed a ship that could carry more supplies for longer voyages, defend itself against hostile forces, and bring back valuable cargo that would justify these expensive expeditions. The answer was the carrack, or as the Portuguese called it, the nao. The carrack was a beast compared to the caravel. We're talking about ships that could be 100 to 120 feet long, with multiple decks and the capacity to carry 200 to 600 tons of cargo. These were the heavy haulers of the Age of Discovery. But don't let the size fool you. The carrack was still a sophisticated piece of engineering. One of the most distinctive features of the carrack was its high forecastle and sterncastle, those tower-like structures at the front and back of the ship. Now I know what you're thinking. Wouldn't those make the ship top-heavy and unstable? And you'd be right to worry about that. Medieval ships with excessive castles were indeed prone to capsizing, but Portuguese engineers solved this problem through careful design. The hull of the carrack was built with a rounded, fuller shape than the caravel, giving it greater stability and displacement. The physics principle here is metacentric height, basically the relationship between a ship's center of gravity and its center of buoyancy. By keeping the center of gravity low through proper weight distribution and ballast, while the fuller hull provided strong buoyancy, the carrack remained stable despite those tall castles. Those castles weren't just for show. The forecastle provided a platform for archers and later for small cannons, giving the ship defensive capabilities. The sterncastle housed the captain's quarters and provided an elevated position for navigation and command. In battles or encounters with pirates, having the high ground was a massive tactical advantage. The carrack also featured a complex sail configuration, typically 3 or 4 masts with a combination of square and lateen sails. The foremast and mainmast carried large square sails for maximum power, while the mizzenmast had lateen sails for maneuverability. Some larger carracks even had a 4th mast, the Bonaventure mizzen, with another lateen sail. This gave the ship an incredible range of sailing options. The rigging on these ships was a marvel of engineering in itself. We're talking about hundreds of lines, each with a specific purpose: halyards to raise sails, sheets to control sail angles, braces to adjust the yards. The sailors had to know this system intimately and in the dark, in a storm, when lives depended on it. The mechanical advantage provided by the pulley systems allowed a relatively small crew to control these massive sails. What really impresses me is how the carrack balanced seemingly contradictory requirements. It needed to be large enough for ocean voyages lasting months, yet maneuverable enough to navigate harbors and coastal waters. It needed to carry heavy cargo and weapons, yet remain seaworthy in rough conditions. It needed to be strong enough to withstand Atlantic storms, yet flexible enough that the hull wouldn't crack under stress. The Portuguese solved these engineering challenges through centuries of accumulated knowledge, trial and error, and incremental improvements. Here's a terrifying thought. You're 3 weeks out at sea, you haven't seen land since you left, and you need to know exactly where you are and which direction to sail. Get it wrong, and you could miss your destination by hundreds of miles, run out of food and water, or sail directly into rocks you never saw coming. This wasn't just an engineering challenge, it was a matter of life and death. The Portuguese didn't invent navigation, but they systematized it and turned it into a science. Let me walk you through how they did it. First, there's celestial navigation, using the sun, moon, and stars to determine your position. The key instrument here was the astrolabe, which Portuguese sailors adapted for maritime use. An astrolabe measures the angle between a celestial body and the horizon. By measuring the sun's angle at noon, for example, you can determine your latitude, how far north or south you are from the equator. The math behind this is elegant. The Earth is roughly spherical, and as you move north or south, the angle of the sun at noon changes predictably. At the equator, during the equinoxes, the sun is directly overhead at noon, 90 degrees. Move north, and that angle decreases. Portuguese navigators used tables that showed the sun's declination for each day of the year, allowing them to calculate their latitude from their measurements. But here's the catch. Determining longitude, your east-west position, was nearly impossible with the technology of the time. You needed accurate clocks to measure the time difference between your location and a reference point, and mechanical clocks of the 15th and 16th centuries weren't nearly precise enough for this. So Portuguese navigators relied on a technique called dead reckoning for longitude. Dead reckoning is brilliant in its simplicity. You keep track of your direction using a magnetic compass and estimate your speed to calculate how far you've traveled. The compass, which the Portuguese adopted and improved from earlier Chinese and European designs, used Earth's magnetic field to point north. Speed was estimated using a chip log, a piece of wood thrown overboard, attached to a rope with knots tied at regular intervals. By counting how many knots passed through your hands in a set time, you could estimate your speed. That's where we get the term knots for nautical speed. The Portuguese also developed detailed navigational charts called portolan charts, which showed coastlines, harbors, compass directions, and navigational hazards. These charts were continuously updated based on the observations of returning sailors, creating an ever-improving database of geographical knowledge. This was early crowdsourcing. Each voyage contributed data that made future voyages safer. Prince Henry the Navigator, though he wasn't actually a navigator himself, established a school or center in Sagres where cartographers, astronomers, and experienced sailors could share knowledge and train new navigators. This institutional approach to navigation was revolutionary. Instead of knowledge being passed down individually from master to apprentice, it was being systematized, recorded, and taught to many. This accelerated the pace of discovery enormously. One innovation I find particularly clever is the Regiment of the North Star. Portuguese navigators developed tables showing the relationship between the height of Polaris, the North Star, and latitude. This gave them a reliable way to determine their position at night, independent of the sun. In the southern hemisphere, where Polaris isn't visible, they developed similar techniques using the Southern Cross constellation. Let's talk about what kept these ships from breaking apart when a massive wave hit them or when they encountered the full force of an Atlantic storm. The ocean is brutal, and wood, for all its advantages, has limits. The engineering that went into Portuguese hull design is absolutely fascinating. The backbone of any ship is its keel, the long structural beam that runs along the bottom from bow to stern. The Portuguese used massive timbers for the keel, often from a single tree, to ensure strength and continuity. This keel did more than just provide structure. It also gave the ship directional stability. The deeper the keel, the less the ship would drift sideways when sailing. It's like the fin on a surfboard. It keeps you going straight. Attached to the keel were the ribs or frames of the ship, which curved up to form the hull's shape. These weren't just randomly placed. Portuguese shipbuilders understood through experience that the spacing and curvature of these ribs affected both the ship's strength and its sailing characteristics. Closer spacing meant a stronger hull that could resist twisting and flexing, but it also meant more weight. Too much weight, and the ship would sit lower in the water and sail more slowly. The technique of carvel planking I mentioned earlier wasn't just about smooth hulls. It also had structural advantages. When planks are laid edge to edge and fastened to the frames, the entire hull acts as a unified structure, distributing stress across a larger area. When a wave hits, that force is transmitted through the planks to the frames and keel, rather than concentrating at weak points. It's an early application of what we now call stressed skin construction. To make the hull watertight, shipbuilders used a process called caulking. They would drive oakum, basically old rope fibers, into the seams between planks using special tools, then seal it with pitch or tar. This created a flexible, waterproof seal that could accommodate the slight expansion and contraction of the wood as it got wet and dried. The quality of caulking could make the difference between a seaworthy vessel and one that leaked constantly. Portuguese shipbuilders also understood the importance of flexibility. A completely rigid ship would crack under the stresses of the ocean. Instead, they built ships that could flex and twist slightly, absorbing the energy of waves rather than resisting them completely. This is the same principle used in earthquake-resistant buildings today. Controlled flexibility is stronger than rigidity. The shape of the hull was optimized through generations of refinement. The bow needed to be shaped to cut through waves efficiently, reducing the impact force and allowing water to flow smoothly along the sides. The stern needed to provide good hydrodynamics while leaving smooth water for the rudder to work in. The bottom of the hull was curved to provide stability while minimizing drag. All of this was achieved through accumulated practical knowledge without the benefit of modern fluid dynamics calculations. Building a ship that could survive ocean voyages required not just good design, but also the right materials, and the Portuguese became masters at selecting and using what nature provided. Let me take you into the shipyards where these vessels were born. The primary material was, of course, wood, but not just any wood. Different parts of the ship required different types of timber with specific properties. For the keel and frames, shipbuilders preferred oak, specifically the varieties that grew in Portugal and imported from northern Europe. Oak is incredibly strong and resistant to rot, especially when kept wet. It has a high density and interlocking grain structure that resists splitting. These properties made it ideal for the parts of the ship that bore the most stress. For planking, Portuguese shipbuilders often used pine, which was lighter than oak and more abundant. Pine planks were easier to work with, and when properly treated and maintained, could last for years. The lower density also meant the overall ship weight could be reduced without sacrificing too much strength, improving performance. The masts required special consideration. They needed to be tall, straight, and strong enough to support the weight of the sails and rigging, while flexible enough to bend without breaking in strong winds. For this, shipbuilders sought out tall pines or firs with minimal knots and straight grain. These trees were so valuable that in some regions the best specimens were reserved by royal decree for shipbuilding. Rope and cordage were critical components, and making them was an industry unto itself. Hemp was the primary material, twisted into strands and then laid up into ropes of various thicknesses. A large carrack might use several miles of rope in its rigging. The strength of rope was crucial. A broken line at the wrong moment could mean a lost sail, a broken mast, or even lives lost. Rope makers developed techniques to create cordage that was both strong and flexible, understanding through practice the optimal twist angles and strand counts. Iron was used sparingly but strategically. Nails and spikes held the planks to the frames, while iron bolts secured critical joints. The quality of iron was variable in this period, and ship's smiths had to be skilled at forging and shaping it. Too brittle, and the iron would crack. Too soft, and it would deform under stress. Corrosion was a constant enemy, as salt water aggressively attacks iron. Some nails were made from copper or bronze for underwater use, as these metals resist corrosion better, though they were more expensive. Pitch and tar, distilled from pine resin, served multiple purposes. They waterproofed the caulking, protected wood from rot and marine organisms, and sealed the rope to preserve it. The smell of a working ship, that mixture of tar, salt, and wood, must have been distinctive and powerful. One fascinating aspect is how shipbuilders preserved knowledge about materials. There were no materials science textbooks, no standardized testing procedures. Instead, knowledge was passed down through apprenticeships and guilds. A master shipbuilder would know by sight, touch, and even smell which timber was suitable for which purpose. They would know how different woods behaved when wet, how they dried, how they aged. This empirical knowledge, accumulated over generations, was just as valuable as any modern engineering manual. We've talked a lot about the engineering of these ships, but a ship is nothing without its crew. The human element of these voyages was just as important as the technology, and the conditions these sailors endured were extraordinary by modern standards. A typical caravel might have a crew of 20 to 30 men, while a large carrack could carry 200 or more. These weren't just sailors in the modern sense, they were a diverse group with specialized roles. You had the captain, who was often a nobleman or experienced navigator, in overall command. The pilot was responsible for navigation and charting the course. The master was in charge of the day-to-day sailing of the ship, commanding the crew and managing the sails and rigging. Then there were the common sailors, the ones who climbed the rigging, hauled on lines, stood watch, and did the hard physical labor that kept the ship moving. Many of these men were young, some barely teenagers, learning the trade through brutal first-hand experience. There were also specialized roles: carpenters to repair damage, caulkers to maintain the hull's integrity, coopers to maintain the barrels that held water and food, and gunners if the ship was armed. Living conditions were harsh beyond what most of us can imagine. There was no privacy, minimal sanitation, and constant dampness. Most crew members slept where they could find space on the deck or below, often in shifts, since there wasn't room for everyone to lie down at once. The diet consisted mainly of hardtack, a type of hard, dry biscuit that could last for months, salted meat, dried fish, and when available, wine or beer, which kept better than water. Fresh water was a constant concern. Stored in wooden barrels, it would often go stale or become contaminated. Sailors rationed it carefully, and running low on water was one of the most feared scenarios on a long voyage. Scurvy, caused by vitamin C deficiency, was a deadly threat on long voyages. Portuguese sailors would have suffered from this disease, though they didn't understand its cause. Some empirical knowledge existed about bringing fresh fruit like oranges and lemons, but consistent preventative measures wouldn't be developed until centuries later. The work was relentless and dangerous. Climbing up rope ladders to the top of a mast while the ship pitched and rolled in heavy seas, then working on a yard to reef or change sails. This required not just courage, but extraordinary physical strength and coordination. Men fell to their deaths, were swept overboard by waves, or were crushed by shifting cargo. Fingers were lost to pinching lines, and hernias were common from the constant heavy lifting. Yet despite these hardships, there was also a sense of camaraderie and shared purpose. These men were doing something unprecedented, exploring unknown waters, discovering new lands, and expanding the boundaries of the known world. The shared danger and hardship created bonds, and there was pride in their skills and accomplishments. The officers and educated men aboard kept detailed logs and journals, recording positions, weather conditions, landmarks, and observations. These documents were crucial for navigation and for future voyages. Some sailors showed remarkable observational skills, noting ocean currents, prevailing winds, the behavior of birds and fish, and other phenomena that helped build the body of knowledge about the seas. Portuguese ships also sometimes carried priests, who served spiritual needs but also often chronicled voyages. Scientists and naturalists occasionally joined expeditions to study new lands. These voyages were floating centers of knowledge gathering, bringing back not just trade goods, but information about geography, peoples, cultures, flora, and fauna. The psychological toll of these voyages shouldn't be underestimated. Months at sea, out of sight of land, with no communication with home, facing daily dangers. This tested men's mental endurance as much as their physical stamina. Superstition was common, and sailors looked for omens and signs. Yet they also developed a pragmatic toughness, an ability to face fear and uncertainty with determination. So there you have it. The incredible science and engineering behind Portuguese ships that changed the world. From the revolutionary design of the caravel to the sophisticated navigation techniques, from the careful selection of materials to the courage of the crews who sailed these vessels into the unknown. What strikes me most about this story is how these achievements emerged from a combination of inherited knowledge, innovative thinking, careful observation, and relentless trial and error. The Portuguese didn't have computers, advanced mathematics, or modern materials science, yet they solved complex engineering problems that allowed them to cross oceans and connect continents. These ships were the cutting-edge technology of their time, the equivalent of space shuttles or deep-sea submersibles today. They represented the frontier of what was possible, and they pushed that frontier further than anyone thought imaginable. The age of discovery wasn't just about brave explorers, it was about brilliant engineering and the systematic application of scientific principles, even before science as we know it was fully formalized. The legacy of these ships extends far beyond the 15th and 16th centuries. The principles of ship design developed by the Portuguese influenced naval architecture for centuries afterward. The navigational techniques they pioneered laid the groundwork for all future ocean navigation. The maps and charts they created became the foundation for understanding global geography. Even the global trade networks and cultural exchanges they initiated continue to shape our world today. But beyond the historical impact, there's something inspiring about this story for us today. These shipbuilders and sailors faced seemingly impossible challenges with limited technology and incomplete knowledge, yet they persevered and succeeded through ingenuity, courage, and determination. They remind us that human innovation can overcome tremendous obstacles when we combine knowledge, creativity, and the will to push beyond what we know. In our modern world, we often take for granted the technology that surrounds us. We use GPS without thinking about the satellites and mathematics that make it work. We cross oceans in hours by plane without considering the generations of knowledge that made flight possible. Looking back at Portuguese ships helps us appreciate that every technology we enjoy today stands on the shoulders of countless innovations from the past. It also reminds us that some of the most important breakthroughs come not from lone geniuses, but from communities of practice. Shipbuilders, sailors, navigators, and merchants, all contributing their expertise and experience to create something greater than any individual could achieve alone. The Portuguese Age of Discovery was a collective effort, building on knowledge from Islamic scholars, Chinese innovations, and European traditions, then adding their own refinements and discoveries. As we face our own challenges today, whether in engineering, science, or any other field, we can draw inspiration from these earlier pioneers. They show us that careful observation, systematic experimentation, and the willingness to learn from both successes and failures can lead to revolutionary advances. They remind us that the impossible is often just the not yet achieved. Before I wrap up, I want to hear from you. What aspect of Portuguese ship engineering impressed you most? Was it the caravel's revolutionary design, the sophisticated navigation techniques, or maybe the incredible courage of the crews? Drop a comment below and let me know your thoughts. And if you enjoyed this deep dive into historical engineering, make sure you're subscribed to this channel because we've got so much more amazing content coming your way. Hit that subscribe button, smash the like button if you learned something today, and comment with your favorite fact from this video. Your engagement helps this content reach more people who share our passion for understanding the brilliant engineering that shaped our world. Thank you so much for joining me on this journey through the Age of Discovery. Until next time, keep exploring, keep learning, and keep appreciating the amazing ingenuity of the human spirit. See you in the next video.